To give a machine spatial intelligence, we have to teach it to instantly convert flat, unstructured 2D images into mathematically precise 3D environments. For decades, the standard approach was structure from motion, or SFM. Systems like Colmap rely on painstakingly slow, iterative processes to match individual pixels across images and triangulate camera positions. Recently, the field shifted toward feed-forward transformers. These models process multiple views jointly, bypassing manual feature matching to predict dense 3D geometry in a single computational pass. But this speed comes at a severe cost. To achieve state-of-the-art accuracy, models like Depth Anything 3 and VGGT have scaled their architectures to over 1 billion parameters. Relying on sheer network depth to brute force geometric reasoning creates a massive memory footprint. It locks advanced 3D reconstruction behind high-end hardware and creates an unsustainable computational trajectory for vision foundation models. Researchers have realized that the contiguous layers of these deep transformers often perform highly similar operations. They aren't learning new features at every layer. They are effectively executing redundant, iterative refinement algorithms across the depth of the decoder. This insight led a team from NVIDIA and ETH Zurich to develop the Déjà View architecture. Instead of stacking distinct layers, Déjà View forces explicit iteration by applying a single shared weight transformer block repeatedly over the exact same data. By reusing identical weights for multiple refinement steps, the architecture eliminates millions of layer-specific parameters. The resulting model requires only 117 million parameters, yet it matches or outperforms feed-forward baselines that are 10 times its size on major 3D reconstruction benchmarks. By making iterative refinement an explicit architectural choice, the researchers provide a direct path toward high-fidelity 3D reconstruction without the massive parameter inflation typical of recent foundation models. The pipeline begins with a continuous, unordered sequence of 2D images depicting a specific scene. These images are passed through a shared Dino v2 backbone. The encoder maps each image into a grid of distinct patch tokens, establishing the baseline feature representation. To manage artifacts and spatial tracking, the sequence is prepended with 2 specific learnable elements, 4 register tokens to absorb non-essential background information, and a distinct camera token to track the viewpoints. The network predicts a per-pixel depth map and a dense ray map. Multiplying the ray's unnormalized direction by the depth scaler plots a precise 3D point. Across the entire grid, hundreds of rays project simultaneously to generate a dense 3D point cloud. Regressing these continuous mathematical vectors and depth maps directly from the image features yields a vastly more accurate geometric representation than attempting to predict rigid, low-resolution 3D voxels. The engine driving this network is the recurrent looped block, which processes the token sequence k times. Inside the block, a dual attention mechanism alternates between frame attention, which processes individual views independently, and global attention, which enables cross-view reasoning. Applying identical weights repeatedly introduces a critical vulnerability. Without temporal context, the block applies the exact same transformation blindly, causing the state vector to loop infinitely or collapse. The solution is continuous time interval conditioning. Sinusoidal time embeddings inject into the block, generating scale vectors S-attention and SMLP. Layer norm and layer scale interact with these to gate residual updates, while S-out scales the updated state vector before feeding it back into the loop. This structure behaves like a learned optimizer, executing steps similar to gradient descent, rather than a traditional static neural network filter. The looping block survives k iterations specifically because these time-conditioned scale vectors dynamically modulate the severity of the shared weights updates. What happens to the internal vector space over k iterations? This dual-axis chart shows the state norm's magnitude growing monotonically. It doesn't contract to a fixed point. However, the cosine similarity shows the vector's direction rapidly stabilizing, pointing directly toward the final geometric target. The researchers call this directional refinement. Because the final decoder utilizes an initial layer norm operation, the magnitude growth is absorbed, meaning only the correct direction of the vector impacts the output. Maintaining this stability requires an expansive pipeline. The model learns from 28 datasets covering synthetic renders, drone flights, and street-level captures. This creates a dataset imbalance. Certain synthetic sets contain 11 million images, while critical, high-quality real-world datasets hold only 10,000. To prevent large datasets from skewing the geometry, the pipeline uses temperature sampling. This mathematically limits massive datasets and intentionally oversamples the small ones, enforcing uniform geographic and spatial diversity. Crucially, the model does not train on a fixed number of loops. Through variable K training, the pipeline dynamically samples the iteration count K from a beta distribution between 8 and 16 for every single batch. By training across a range of iterations, variable K transforms the iteration count into an inference time compute dial. Users can deploy a single checkpoint and seamlessly trade millisecond latency for higher fidelity on the fly. To prove its efficacy, this scatterplot charts parameter count against accuracy. Depth Anything 3 and VGGT sit far right at 1.2 billion parameters, around 84%. Déjà View plots far left at just 117 million parameters, climbing above 85%, outperforming the giants. This small parameter count translates directly to peak memory efficiency. Déjà View processes 24 distinct high-resolution camera views using under 5 gigabytes of memory. To verify that the looping mechanism itself is responsible for this performance, the team ran an ablation study. They trained an identical architecture using independent, unshared weights for every step instead of a loop. Operating on the exact same compute budget and training data, the looping shared weight model definitively outperformed the parameter-heavy independent model. Embedding explicit iteration into the architecture provides a superior inductive bias for 3D geometry compared to raw parameter capacity. The model does have physical boundaries, specifically the phenomenon of extrapolation failure. If the compute dial is pushed too far, running 30 iterations when trained on a maximum of 16, the feature channels rapidly diverge and the 3D geometry collapses. The model also assumes a static weld. It does not explicitly calculate the physics of moving objects within dynamic scenes. We are left with 3 distinct conclusions. First, deep feed-forward networks are wasting billions of unique parameters, simulating basic iterative refinement. Second, applying a single looping transformer block with time-conditioned routing achieves state-of-the-art multi-view reconstruction with a fraction of the hardware footprint. Third, variable K training creates highly flexible, compute-adaptive models capable of adjusting to edge deployment environments on the fly. Architectures like Déjà View suggest that spatial computing can become accessible through efficient, shared-weight designs that prioritize architectural inductive bias over raw computational brute force. If you found this breakdown useful, hit subscribe, and we'll see you in the next episode.